All right, let's explore. Number 10, the hierarchy problem. In 1974, physicists Howard Georgi and Sheldon Glashow were working toward a grand unified theory of nature's fundamental forces when they ran directly into a number that refused to make sense. Gravity, the force holding galaxies together, the force keeping your feet on the ground, is at least 10 trillion times weaker than electromagnetism. The math was right. The implication was staggering. To understand how absurd this is, consider a simple demonstration that physicists use to this day. A small refrigerator magnet can lift a paperclip off a table, overcoming the entire gravitational pull of planet Earth acting on that paperclip. One tiny magnet defeats a planet. The forces of nature are supposed to be facets of the same underlying reality. They should be remotely comparable. They are not even close. This gap is known as the hierarchy problem, and it sits at the heart of modern physics like a splinter that cannot be removed. The Standard Model, the most successful theory in scientific history, has no explanation for why gravity is so catastrophically weak compared to every other force. The numbers simply don't belong in the same equation. In 1998, physicists Nima Arkani Hamed, Savas Dimopoulos, and Giadavalli proposed a radical solution. Gravity might appear weak because it is leaking. Their model suggested that gravity operates across extraspatial dimensions too small to detect, bleeding away into hidden geometries, while the other forces remain confined to the dimensions we experience. The Large Hadron Collider at CERN was partly designed to find traces of these extra dimensions. It has found nothing. The hierarchy problem is not a mystery at the edge of physics. It is a contradiction at its foundation. Something is profoundly wrong with our picture of the forces governing reality, and after decades of searching, we are no closer to knowing what it is. Number 9. The quantum measurement problem. In October 1927, the greatest physicists alive gathered at the Fifth Solvay Conference in Brussels to confront a result that none of them could fully accept. Experiments with electrons had revealed something that violated every assumption about how the physical world works. A particle, before it is observed, does not have a definite position. It does not have a definite speed. It does not have a definite state of being. These are not gaps in our knowledge. The particle is genuinely, physically undefined. For centuries, science operated on a clear assumption. Things exist in specific states, whether or not anyone is looking at them. A planet occupies a position in its orbit at every moment. A thrown stone follows a determined path. Observation, in this view, simply reads out what is already there. Quantum mechanics shattered that assumption completely, and no one was more resistant to accepting it than Albert Einstein, who famously wrote in a 1926 letter to Max Born that he could not believe God plays dice with the universe. The double-slit experiment demonstrates the problem with brutal clarity. Fire single electrons one at a time through two slits, and they build up an interference pattern on the detector behind them, as if each individual electron passed through both slits simultaneously as a wave. Place a detector at the slits to observe which one the electron passes through, and the interference pattern vanishes. The electron becomes a particle again. The act of observation changes the physical outcome. Niels Bohr's Copenhagen interpretation, formalized in 1927, concluded that particles exist in superposition, a blur of all possible states, until measurement forces a single outcome. Hugh Everett proposed in his 1957 Princeton doctoral thesis that measurement doesn't collapse the wave function, but instead splits reality, creating branching parallel universes where every outcome occurs. In 2019, researchers at the University of Vienna demonstrated quantum superposition in molecules containing nearly 2,000 atoms, suggesting this is not a phenomenon confined to the subatomic. The measurement problem remains unresolved. Every time you look at the night sky, You are not passively witnessing a universe that already existed in a defined state. You are, in some small but physically real sense, participating in the act of deciding what it is. Number 8. Olbers' paradox. In 1823, German astronomer Heinrich Wilhelm Olbers posed a question so deceptively simple that many dismissed it as barely worth asking. If the universe is infinite and filled throughout with stars, then in every direction you look, your line of sight must eventually land on the surface of a star. The entire night sky should blaze with the combined light of an infinite number of suns. It should be impossible for any patch of sky to be dark. And yet, every night, you step outside and find darkness. The question had troubled astronomers long before Olbers gave it his name. Thomas Digges raised a version of it in 1576, and Johannes Kepler noted it as a puzzle in 1610. If the universe stretched infinitely in all directions and had existed forever, the sky at night should be as bright as the surface of the sun. This was not a minor observational nuance. It was a fundamental contradiction between cosmological assumptions and the simplest experience of being alive on Earth at night. The most remarkable early response came not from a physicist, but from a poet. In his 1848 prose poem Eureka, Edgar Allan Poe suggested that the darkness of the sky implied the universe was finite in age. Light from the most distant stars simply had not had time to reach us. He was, in broad strokes, correct. More than a century before, astronomers had the tools to confirm it. The modern resolution involves two factors. The universe is approximately 13.8 billion years old, limiting how far light can have traveled to reach us. And the expansion of the universe redshifts the light from the most distant sources beyond the visible spectrum, rendering it invisible to the naked eye. The observable universe contains an estimated 2 trillion galaxies, according to a 2016 study led by Christopher Consolis at the University of Nottingham, and the light from the farthest of them has been stretched into radio waves and microwaves we cannot see. The darkness of the night sky is not simply empty space. It is direct, empirical evidence, encoded in the most ordinary observation imaginable that the universe has a beginning, and that its history is finite. The deepest truths about cosmic structure have been hiding in plain sight above us every clear night for all of human history. Number 7. The fine-tuning problem. Sometime in the latter half of the 20th century, physicists began cataloging the fundamental constants of nature, the fixed numbers baked into the universe's architecture, things like the strength of gravity, the mass of the electron, the rate of nuclear reactions inside stars. There are approximately 26 of these dimensionless constants. None of them can be derived from any deeper theory. They simply are what they are. And when researchers began asking what would happen if they were even slightly different, the answers were deeply unsettling. Astronomer Martin Rees outlined the problem with stark clarity in his 1999 book, Just 6 Numbers. He identified 6 fundamental constants whose precise values determine whether a universe can contain stars, planets, atoms, or anything at all. If the nuclear force were 2% stronger, hydrogen would have fused into helium in the early universe, leaving no fuel for stars. If it were slightly weaker, protons could not bind, and chemistry would be impossible. The tolerances are razor thin, and physics has no explanation for why the values landed where they did. In 1953, astronomer Fred Hoyle made one of the most remarkable predictions in the history of science. He reasoned that carbon, the backbone of all known life, could only be produced in stellar interiors if the carbon-12 nucleus had a resonance energy at a very specific level. Without it, carbon would not accumulate in stars, and life as we know it could not exist. He predicted the resonance before it was measured. Physicist Willie Fowler's group at Caltech subsequently confirmed it experimentally. The cosmological constant, representing the energy density of empty space, is fine-tuned to approximately 1 part in 10 to the power of 120. Roger Penrose calculated that the probability of the universe beginning in its observed low-entropy state by pure chance is 1 in 10 to the power of 10 to the power of 123. These are not numbers that emerge naturally from physics. They are numbers that had to be set to extraordinary precision before the universe could contain anything. The constants of nature are not laws that physics discovered by examining the universe. They are numbers written into the fabric of reality before physics existed, calibrated with a precision that has no physical explanation, pointing toward a question that science has not yet found the language to answer. Number 6. The black hole information paradox. In 1974, Stephen Hawking published a paper in the journal Nature with the deceptively modest title Black Hole Explosions, and detonated a crisis in theoretical physics that has not been resolved in the 50 years since. Hawking demonstrated that black holes are not, in fact, perfectly black. They emit a slow trickle of thermal radiation due to quantum effects near the event horizon, radiation that carries no information about whatever fell into the black hole to produce it. Given enough time, a black hole would evaporate completely. And when it did, everything that had ever fallen into it, every particle, every quantum state, every piece of physical information would be permanently gone. The problem is that this is forbidden. Quantum mechanics, the most precisely tested theory in the history of science, is built on a principle called unitarity, the requirement that information can never be destroyed. Information can be scrambled beyond any practical hope of recovery, but the underlying data must be preserved somewhere in the quantum state of the universe. Hawking's calculation, derived from equally well-tested general relativity, said otherwise. The two pillars of modern physics were directly and irreconcilably contradicting each other. In 1997, Hawking and physicist Kip Thorne made a formal bet with John Preskill of the California Institute of Technology, wagering a set of encyclopedias against the proposition that information could escape a black hole. In 2004, Hawking publicly conceded, acknowledging that information likely escapes through subtle correlations in Hawking radiation. Most physicists considered the concession premature. The mechanism by which this might happen remains stubbornly unclear. In 1997, theoretical physicist Juan Maldacena proposed the ADS-CFT correspondence, a mathematical framework suggesting that a black hole's interior might be fully encoded on its two-dimensional event horizon, like information on the surface of a hologram. This holographic principle offered a potential route to resolving the paradox, but it applies cleanly only in a specific geometry of spacetime that may not match our universe. As of today, no complete consensus resolution exists. If black holes destroy information, then quantum mechanics is wrong. If they don't, then our understanding of general relativity breaks down at the event horizon. One of the two frameworks underlying all of modern physics contains a fatal flaw, and we cannot currently determine which one or whether fixing it will require dismantling both. Number 5. The antimatter asymmetry. In the first fraction of a second after the Big Bang, the laws of physics, as we understand them, required that equal amounts of matter and antimatter be created. When matter and antimatter meet, they annihilate each other in a flash of pure energy, completely and without remainder. If the early universe was perfectly symmetric, every matter particle should have found its antimatter partner. The annihilation should have been total. The result should have been a universe of light, with no atoms, no stars, no planets, and nothing capable of asking why. Instead, here you are. The expectation of perfect symmetry was not an assumption physicists made carelessly. It followed from some of the most fundamental symmetry principles in quantum field theory. The universe, at the moment of its birth, should have had no preference for one type of matter over the other. Yet the universe we observe contains only matter. The antimatter is simply gone, and physics has no complete explanation for where it went or why it left. In 1964, physicists James Cronin and Val Fitch at Brookhaven National Laboratory discovered a subtle asymmetry in the behavior of certain particles called kaons. Matter and antimatter, it turned out, did not behave in precisely identical ways under all conditions. This phenomenon, called CP violation, earned Cronin and Fitch the Nobel Prize in Physics in 1980. It proved that nature has a preference, however slight, for matter over antimatter. But the magnitude of CP violation measured in the Standard Model is vastly, catastrophically insufficient to account for the asymmetry we observe. The known physics explains perhaps a billionth of the necessary imbalance. For every billion antimatter particles created in the early universe, there appear to have been 1,000,000,001 matter particles. That single extra particle in every billion survived the annihilation to become everything you have ever seen or touched. The T2K experiment in Japan, operational since 2010, and the LHCb detector at CERN are actively searching for additional sources of CP violation that could close the gap between theory and observation. They have not yet found what they need. Your existence is not something the laws of physics predicted or required. It is a deviation from them, a rounding error in the accounting of the early universe, a surplus of matter so inexplicably slight that physics has spent decades failing to explain it. Every atom in your body is a remnant of an asymmetry that should not have been there. Number 4. The Cosmic Horizon Problem. In 1965, physicists Arno Penzias and Robert Wilson at Bell Laboratories in New Jersey were attempting to eliminate a persistent hiss from a large horn-shaped antenna when they realized they were not detecting interference at all. They were hearing the faint thermal afterglow of the Big Bang itself, a uniform signal pervading the entire sky at a temperature of 2.725 Kelvin. Penzias and Wilson received the Nobel Prize in Physics in 1978, but hidden inside their discovery was a paradox that would take decades to confront seriously, and whose proposed solution remains unconfirmed to this day. The cosmic microwave background radiation is the same temperature in every direction, to within 1 part in 100,000. That uniformity sounds reassuring until you calculate the distances involved. The observable universe is approximately 93 billion light-years in diameter. Regions of the CMB on opposite sides of the sky are separated by distances so vast that, given the age of the universe, light could never have traveled between them. They have been moving apart since the earliest moments of existence. They have been causally disconnected since before atoms existed. They could never have exchanged heat, energy, or any physical signal. They should not be the same temperature. They are identical. This is the horizon problem, and it implies that either our understanding of the early universe is wrong, or something occurred in the first moments of cosmic history that connected everything before the distances grew too great. In 1980, physicist Alan Guth proposed that the universe underwent a period of exponential expansion called inflation, beginning approximately 10 to the power of negative 36 seconds after the Big Bang. In this model, everything we can observe today originated from a region so tiny that it was fully causally connected, then was stretched to cosmic scales faster than the speed of light, before expansion slowed to its current rate. Inflation is compelling. It explains not only the horizon problem, but also the flatness of the universe's geometry and the distribution of galaxies across the large-scale structure of the cosmos. But it has not been directly confirmed. The clearest predicted signature of inflation, primordial gravitational waves detectable as a specific polarization pattern in the CMB called B modes, has been searched for extensively by the BICEP-2 collaboration and the ESA's Planck satellite without definitive detection. The universe's most striking large-scale feature, its seamless uniformity across distances that should have no physical connection, is explained by a process that occurred in the first unimaginable fraction of a second of existence, at energies no instrument can reach, and that has left no confirmed observational trace. The solution to the paradox exists, if it exists at all, in a moment of cosmic history we cannot directly see. Number 3. Quantum foam. In 1955, physicist John Archibald Wheeler sat with the equations of quantum mechanics and general relativity and followed them to their natural conclusion at the smallest possible scale. At a distance of 1.616 times 10 to the power of negative 35 meters, a scale known as the Planck length, space itself should cease to behave like space. The Heisenberg uncertainty principle, applied to space-time geometry at this resolution, produces energy fluctuations so violent that the fabric of space should be churning, foaming, forming, and dissolving microscopic wormholes and topological structures faster than any measurement could catch them. Wheeler called it quantum foam. The smooth, continuous space through which planets orbit and light travels should not exist at its most fundamental level. To appreciate how small the Planck length is, consider that a proton is already incomprehensibly tiny, too small to see with any optical instrument. The Planck length is roughly 10 to the power of 20 times smaller than a proton. It is not merely beyond the reach of current technology. It is beyond the reach of any technology that current physics can envision. No particle accelerator built on plausible principles could probe distances anywhere near the Planck scale. Wheeler's quantum foam is a theoretical necessity that may never be directly observed. The idea is not a fringe speculation. It follows from mainstream physics. Both loop quantum gravity and string theory independently predict that spacetime has a discrete, granular structure at the Planck scale, rather than the smooth continuum that every equation in classical and relativistic physics assumes. These two theories agree on almost nothing else, but on the breakdown of smooth space at the smallest scales, they converge. Astronomers have searched for indirect signatures of Planck scale structure using gamma-ray bursts among the most energetic events in the universe. If space is grainy at the Planck length, photons of different energies should travel at slightly different speeds as they interact with the underlying texture of spacetime. The Fermi Gamma Ray Space Telescope analyzed a gamma-ray burst in 2009 and published results in Nature that set limits on this effect, finding no measurable dispersion. The 2013 follow-up analysis tightened those limits further. Quantum foam has not been ruled out, but its signature, if it exists, is smaller than the best instruments can resolve. Every measurement ever made in physics, every orbit calculated, every wave function solved, every force described, rests on the assumption that space is a smooth, stable, continuous medium. The equations of physics themselves suggest that assumption fails at a scale we can never directly examine, leaving us to build our entire understanding of the universe on a foundation we cannot see and cannot test. Number 2. The cosmological constant problem. In 1917, Albert Einstein introduced a term into his field equations of general relativity called the cosmological constant, a value representing the energy density of empty space. He added it to make his equations describe a static universe, then discarded it when Edwin Hubble demonstrated in 1929 that the universe was expanding. For most of the 20th century, physicists assumed the cosmological constant was simply zero. Then, in 1998, two independent research teams dismantled that assumption and created the worst numerical crisis in the history of science. The High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, were both measuring the rate at which the universe's expansion was slowing down under the pull of gravity. They expected to find deceleration. Instead, both teams independently found that the expansion was accelerating. Something was pushing the universe apart with increasing force. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011. The mysterious repulsive energy driving the acceleration became known as dark energy, and it constitutes approximately 68% of the total energy content of the universe, according to data from the European Space Agency's Planck satellite. When physicists turned to quantum field theory to calculate what the energy density of empty space should be, they got an answer. The answer was 10 to the power of 111 joules per cubic meter. The measured value is approximately 10 to the power of -9 joules per cubic meter. The discrepancy is a factor of roughly 10 to the power of 120 orders of magnitude. It is by any measure the largest gap between a theoretical prediction and an experimental observation in the history of physics. Steven Weinberg had noted in a landmark 1987 paper in Physical Review Letters that if the cosmological constant were much larger than observed, gravity could never have assembled galaxies, making our existence anthropically impossible. The universe appears calibrated to a tolerance that our best theories cannot begin to explain. The implications extend beyond the present moment. In 2003, physicist Robert Caldwell and colleagues published a paper in Physical Review Letters describing a scenario called the Big Rip, in which dark energy, if it grows over time, will eventually overcome every other force in the universe. First, galaxy clusters will disperse, then individual galaxies, then solar systems, then planets, then the atomic bonds holding matter together, and finally the nuclei of atoms themselves, until the fabric of reality is stretched to nothing. Whether the Big Rip occurs depends entirely on the future behavior of the cosmological constant, which we do not understand well enough to predict. The vacuum of empty space, the baseline of reality itself, the nothing from which everything emerges, is saturated with an energy whose value sits 120 orders of magnitude away from what physics predicts, and whose ultimate behavior will determine the fate of everything that exists. It is not a gap at the edge of knowledge. It is a chasm carved through the center of it, and every cosmological theory built on solid ground must somehow bridge it. Number 1. The Boltzmann brane paradox. In the 1890s, physicist Ludwig Boltzmann was defending his statistical theory of thermodynamics against critics who raised a point he could not easily dismiss. His equations, which described how entropy increases and disorder spreads through physical systems, contained a disturbing implication. In a system that exists for long enough, random fluctuations will eventually produce any configuration of matter, no matter how improbable. A scrambled egg will unscramble. A shattered glass will reassemble. And a fully functioning human brain, complete with every memory, every sensation, every belief about the world, will spontaneously and briefly assemble itself from thermal chaos, without any prior history, without any universe surrounding it, without any physics that preceded the moment of its formation. In 2004, physicists Andreas Albrecht and Lorenzo Sorbo formalized this implication in a paper asking whether the universe could afford inflation. They coined the term Boltzmann brane to describe a self-aware observer assembled by random fluctuation, rather than by the long evolutionary and cosmological history we believe produced us. The question they raised was not merely philosophical. It was a precise technical problem for modern cosmology. In an eternal universe, or in the vast timescales produced by many inflationary models, random fluctuations will occur with a frequency governed strictly by their probability. And the probability of assembling a single conscious brain by fluctuation, while fantastically small, is enormously larger than the probability of fluctuating an entire low-entropy universe, complete with a consistent 13.8 billion year history. In an eternal cosmos, Boltzmann branes vastly outnumber observers who evolved through genuine cosmic history. This is not merely an abstract curiosity. It is a problem that invalidates cosmological theories from the inside. A physical theory whose equations predict that the overwhelming majority of observers, consistent with its premises, are Boltzmann branes experiencing false memories of a universe that never existed, is a theory that destroys its own epistemic foundations. If most observers in your model are hallucinating, then the observations you used to build the model cannot be trusted. The theory eats itself. Physicist Sean Carroll and colleagues have argued that suppressing Boltzmann brain production must be treated as a genuine constraint on viable cosmological models, and the problem has become an active area of theoretical physics research through the 2010s and into the 2020s. The paradox connects simultaneously to the arrow of time, to the anthropic principle, to the foundations of statistical mechanics, to the multiverse, and to the measurement problem in quantum mechanics. No other single problem in physics sits at the intersection of so many fields at once. There is no experiment you can perform to confirm that the universe around you is real rather than a spontaneous quantum fluctuation. You cannot step outside your own experience to verify that your memories correspond to events that actually occurred. The mathematics does not merely fail to rule out the possibility that you are a Boltzmann brain. In many of the most successful cosmological frameworks physicists have constructed, the mathematics actively predicts that something like you is more likely to have assembled from noise than to have emerged from 13.8 billion years of genuine cosmic history. Every paradox in this list, every physicist who identified it, every telescope that gathered the data, every equation written on every chalkboard in every university in the world, and every thought forming in your mind right now as you process these words exists, according to the universe's own mathematics, under a shadow it cannot dispel. There is no observation, no measurement, no proof available from inside experience that separates a mind with a real past from one that flickered into existence a moment ago, complete with the memory of one. The universe built the tools that revealed this problem, and then discovered those same tools cannot solve it. If you want to see more videos like this, click the video on screen now and make sure to subscribe.